Hello and welcome to the third lesson in Unit 2, Normal and Frictional Forces. So, learning goal today, I can determine the normal force acting on an object and calculate the corresponding frictional force. So we're looking at the friction force specifically. So a couple of quick definitions here. What is a frictional force? A frictional force is a force that opposes motion. That opposes motion, and that's it. So when you draw the vector representing friction, it is always drawn opposite to the motion of the object. Motion of the object. All right, so if you have something that is being pulled, so a quick free body diagram, if you have an applied force in this direction, so you're pulling that way, automatically force of friction's that way. If we have a falling object, remember we talked about force due to gravity is pulling the object downward, so it's falling. We talked about air resistance, but really air resistance is a form of friction. So we always write or draw the force due to friction in the opposite direction of the motion. So the coefficient of friction is a ratio of applied force to normal force. Oops. Normal force. So that being said, we write it like this. It's a U with the tail on the front. So you draw a U and put that little tail on the front, and that is our coefficient of friction. So that's the symbol. Coefficient of friction. And we pronounce it mu. Not mu, mu. All right, and it is a ratio of the force of friction compared to the normal force. Okay, so force of friction over the normal force. So up here I had mentioned it's applied force, and we'll talk about it in a little bit more detail, but it is that frictional force. Now mu is always between 0 and 1. Okay, it's always between 0 and 1. And think of it, it's a ratio, so it's a, you can almost, to simplify it, a percentage conversion. So how much of the normal force is being converted to frictional force? So if mu is 0.6, you can think of it kind of as there's a 60% transfer between your normal force to a frictional force. And finally in here, there are two types. Two types of friction. The first one is static friction. And it opposes, oops, I don't know what I was writing there, opposes motion beginning. All right, so if you're going out and pushing your friend's car, you are fighting static friction off the start. Once it gets moving, then you have kinetic friction. That opposes an object in motion. All right, so again, two types of forces, or sorry, two types of friction. We have static friction, which opposes an object to start moving, and kinetic friction opposes an object that's already in motion. And we always write it as mu s for static and mu k for kinetic. And static friction is always greater than kinetic friction. So if you think back to an object, it's always harder to get something rolling than it is to keep it rolling. Okay, and that's because static friction is so much greater. All right. So why is the normal force so important? Well, normal force, again, if we go back to a free body diagram, we have force due to gravity, and when we did the free body diagrams, I said normal force always opposes force due to gravity for an object on the ground. So we can conclude in this case that normal force is equal to gravitational force. So what is the calculation for the force due to friction? So the formula for the force due to friction is mu F times the normal force. Okay? Now, what happens if, so what about, same thing, what happens if we have an object sitting on the ground, there's a force due to gravity, and now you're pushing down on it with some applied force? All right, what about that situation? So the normal force in this case is not, it is equal to gravity, but it's also equal to the applied force down. If you, because of this, the normal force is increased, if the normal force increases, then in this formula, the result will be a bigger force due to friction. Okay? So the greater the normal force, the greater the friction. All right? So I've already talked about types of friction in the previous slide, so you already have that. So let's just talk about rubbing hands together as an example here. Rubbing hands together, if you press lightly, warmth builds up. Okay, so if you just sit there right now and you rub your hands together normally, okay, you can feel the heat generated between your palms. What happens if you press, I'll say press hard together? All right, so now you're putting a little bit more effort into it. Rub your hands again with it closer together, heat builds up quicker. And that's because the friction force is increased. So the heat comes from the friction. So heat builds up or builds faster. Okay? So it's that normal force. The harder two objects are pushed together and you're pulling it along that surface, it becomes more intense or greater force due to friction. So I got an example to finish off this particular note. So we have a 100 kilogram crate. So I'm just going to write my information right here. 100 kilograms for my mass. It's pushed across the floor. So A part. What is the minimum force required to start moving the crate? So the crate's not moving. So I'm going to give myself a diagram. Here's my crate. Force due to gravity. Normal force. I want to push it. And if I push it and it starts to move in the real world, it'll experience friction. So if I want to get it just moving, that means that my FA has to be bigger than the force due to friction. Okay? You have to push harder than the frictional force. So that would mean that we need to know what the frictional force is. And of course we have a formula. The object's not moving, so it's mu s multiplied by the normal force. Because the normal force is equal to gravity, the formula can also be written as mu s multiplied by mass times gravity. Okay? 0.6 is our static coefficient. It's 100 kilograms, 9.81. So if we do that calculation, we get 588 0.6 newtons. So therefore, we must push with more than 588.6. All right, so if you push with 588.7, it will start to move. All right, so you have to beat that or get above that threshold in order to get this object to move. Okay, we need that force of friction greater. B part. What is the minimum force required to continue moving? So we're going to keep that crate moving. It's the same diagram. Okay, now you've got to be careful here because in this case, you don't want to accelerate it. It just says to keep it moving in a constant motion. So that means now our frictional force and applied force have to be the same. All right, so frictional force has to be the same as our applied force. So our frictional force, it's moving, so we have to use mu k multiplied by the normal, which would be mu k times mass times gravity, 0.4 times 100 times 9.81. And from that, we get 0.4 times 100 times 9.81. We get 392.4. So we must push with 392.4 newtons. All right, to keep it moving. All right, at a constant velocity. Now, what happens if we want to accelerate it? So C part, we want to accelerate it at 2 meters per second squared. So we know that from our Newton's second law, unbalanced force creates acceleration. So this is where I'm going to start. What is that unbalanced force going to be? Well, the mass is 100. We want to accelerate it at 2 meters per second squared. So we're going to need 200 newtons of force. So if I go back to my free body diagram, force of friction, applied force, normal, and gravity. In order for this situation right here, we are not accelerating, okay? It's answer to number B. Now, to accelerate, we're going to put an unbalanced force in there. So therefore, our total force that needs to be applied is the unbalanced force to accelerate it, plus the required force to continue or oppose friction. So that means we're going to end up with 200 newtons for the acceleration, plus 392.4 to maintain the motion as is. So that means you're going to have to push with 592 newtons to accelerate it. The part, if you push down on the crate with 100 newtons of force, to demonstrate how the force of friction changes. So I don't really have to, doesn't matter whether we're going to do kinetic or static here. So let's pick kinetic because it's on the move. Force normal. So this time it's going to be our kinetic, and in here it's going to be mass times gravity. So again, the situation where it got gravity pushing down Fg, and now we're applying 100 newtons on top of that. So we're going to have to add 100 newtons to balance out the normal force. So doing our substitution, 0.4 and then 100 times 9.81 plus the 100, we find that our frictional force becomes 432.4 newtons. So above, if you compare it, that value there to that value there, okay, it is requiring more you end up with more frictional force because you have someone sitting on top. Finally, E, if you lift up on the crate, how does that change it? So E part, force due to friction. So now you're pulling up on the cart, and what you're doing is you're making it lighter. So instead, mu k, you have your force of gravity acting downward, but now you're pulling up, so you're making it lighter. So the free body diagram would change. I'm going to have to finish this in about a 2-minute video in the next one. I apologize. And then you can move on.